Okay, and welcome to this video on wave basics. First question is, what is a wave and why are we interested in it? Well, as we can see from a picture very clearly, when we say wave, that's the first thing we think of is the wave in the sea. And what can we do with a wave in the sea? Normally we can go surfing, can't we? Which is pretty cool. So why are we interested in waves in physics then? Because studying waves, it doesn't sound interesting. Going surfing on a wave, now that's cool, but studying a wave, that's not very interesting, is it? So why is it that we're interested in waves? Well, the answer is because things that we don't really understand that are pretty important, such as the way that light moves. If we research water waves and we can understand how waves move and propagate, then we can understand more about light. Light is pretty important, isn't it? It's what gave us life. So, you know, I guess we should try and figure out, try and understand more about it, right? Okay, so waves that move through a material or a vacuum are called progressive waves. Progressive waves transfer energy without transferring matter. In fact, there's two types of waves: progressive waves and stationary waves, or standing waves. Progressive waves transfer energy without transferring matter. What does that mean? It means the wave itself moves along, but the particles of the wave, they just vibrate around an equilibrium position and they don't actually move along the wave. So energy is transferred between particles. The particles themselves, they don't move along the wave, they just vibrate around an equilibrium position. So waves can be mechanical waves if they need a substance medium through which to travel. So this would be the normal situation of a wave when we're talking about particles which are vibrating or oscillating. They would need, you know, the very word particle means that there needs to be something to propagate the wave. Sound is an example of such a wave. So like we said in the beginning of the video, why study waves? We need to understand light, but we also need to understand other phenomena such as sound, right? Things we can't see, but we need very important that we understand them. So by studying waves, we can picture how things like sound might travel. Sound itself, we know, needs a medium, but light doesn't. So light's a very interesting type of wave. It's not a mechanical wave. It doesn't need a medium in which to travel through. Sound, on the other hand, does. And here we can see what progressive wave here. This is a sine wave. Both sound waves and light waves can be plotted as this type of sine wave on a graph. Key things, so we've got wavelength, displacement and amplitude here. A couple of other points, waves can be transverse or longitudinal. So in longitudinal waves, the particles of the medium vibrate parallel to the direction of the wave velocity. In transverse waves, the particles of the medium vibrate at right angles to the direction of the wave velocity. What does that mean? Let's take a look at an example. Here we can explain a bit more about a longitudinal wave. As you can see here, we know in a longitudinal wave that the particles in the medium will be vibrating parallel to the direction of the wave motion. So if we look at the top picture here, we can see that these wave fronts, they are moving from left to right. If we just track one, we can see, isn't it? But if we focus on an individual particle, if we look in the bottom screen, we can just see that the individual particle is moving back and forth in the same direction as where the waves are traveling, but the particles are just moving back and forth, back and forth. So that's a longitudinal wave. Now if we just scroll down and have a look at this picture, this is an example of a transverse wave. If we focus on the top part, we can see that the waves are moving along like that. If we just track one, it's quite hard to track them, but you can see that they move along the top there from left to right. So again, the wave motion is going from left to right, but unlike a longitudinal wave where the particles are just going from left to right, we can see if we focus on just the individual particles, they're just moving up and down. So we say that they are perpendicular to the direction of wave motion. Interestingly, but we don't need to know this, here's an example of a water wave, which is a combination of both a longitudinal and a transverse wave. Here we can see, like a transverse wave, the waves are moving from left to right. But unlike in a transverse wave, the particles are actually moving in a circular motion on the surface there. This is caused by the combination of two mediums. We've got the medium of water and the medium of air here. So you can see that the particles end up going in following a circular motion, and a little bit lower there. Okay, let's have a look at some formulae that we need to know. Frequency equals 1 over period, F equals 1 over T, where F is the frequency and T is the period. F is the number of waves per second. So frequency is the number of waves per second, period is the time taken for one wave. And here is the wave formula that we need to know. Speed of wave, V, equals frequency times wavelength. V equals F lambda. Okay, now we can look at how waves can be represented on a graph. Let me put myself back up the top here. In this one, it's just asking us to determine the wavelength and the amplitude of these two waves, as we've seen on the previous diagram. So we've got a displacement distance graph here. So there's two types of graphs. One can be displacement and distance, one can be displacement and time. On a displacement distance graph, that means that this is the distance the wave has travelled, and this is the displacement of the particles in the medium from their equilibrium position. Here we can see that the maximum displacement of A is 4 centimeters, so the amplitude is 4 centimeters. And if we look at the wavelength, so we want to find this position and then the exact same position on the next wave, boom, is here, dot, 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 dot. The wavelength is 15 centimeters. Okay. If we know the wavelength and we know the speed, we can work out the frequency. If we know the frequency, we can work out the period. So this is a C.R.O screen. This is going to be a common question. Waves can be represented on a C.R.O screen. That just means that they've taken the wave itself and turned it into an electrical signal, which can be represented on a screen. The screen is divided into these sections, which are called divisions. A division might be given as just a division, or it could be given as a distance. In this case, it just says per division. And this is 1 ms per division. So 1 millisecond per division means every division is 1 millisecond. So how can we use that? Well, first of all, a good way to start is to calculate the wavelength, isn't it? So we need to find an easy way to find the wavelength. This doesn't quite cross on a good place here. This one goes smack through the middle. So this one is more or less right there. So if we start there and then we find the exact same point, which is here, then we know that from there to there is one wavelength. And how many divisions is that? 1, 2, 3. 3 divisions, 1 millisecond per division, so it's 3 milliseconds altogether. Sorry, length would be in meters, this is time. So what does that tell us? If one wave takes 3 milliseconds, then that is the period of the wave, t. So t equals 3. I won't write it because it's hard to write with this pen, but t equals 3 milliseconds. And from that, we know that 1 over t is the frequency, so we can just calculate that through. If you pause the video, you can see here the steps involved in that. Yeah, 1 over t equals 1 over 3 times 10 to the minus 3, and that should be seconds there. Okay, so the wave frequency is approximately 330 Hertz, fine. Let's pause the video, and let's see if you can answer one of these questions yourself. This one was the one. Wait. This one was the one. Okay, so just pause the video and have a go at that. Okay, welcome back. When a sound wave is displayed on a C.R.O screen, two complete waves occupy 5 scale divisions. So 2 waves occupy 5 scale divisions. The calibrated time-based setting is 0.005 seconds, or 5 times 10 to the minus 3 seconds, 5 milliseconds per division. Determine the frequency of the wave. Same what we did last time. Let's count. Period is time for one wave, so 0.005 times 2.5, because there's 2.5 divisions there. So 0.005 seconds times 2.5 divisions equals 0.0125 seconds. Frequency is 1 over period, so 1 over 0.0125 equals 80 hertz is the answer. Okay, and I think that's basically all we need to cover. Let's have a look at this, just to check your understanding. Pause the video, see if you can fill in the gaps. Okay, welcome back. The first one is displacement, amplitude, wavelength, period, and the last one is frequency. Okay, thanks for listening. Don't forget to comment if you've got any questions, and subscribe. See you again.